delay. We had trouble with getting the slides connected. Hi, so today I'm going to speak about systemd and specifically what's new in systemd in 2015 and what's going to come in systemd in 2016. I'll do this talk in English, but I hear there's live translation. I tend to speak quite fast, so I'm sorry for that already. If I'm speaking too fast, just let me know and I'll try to slow down again. In my talk, I generally prefer questions right away so that we can make this interactive. So if you have a question, feel free to interrupt me, and we can discuss that right away. The talk is really just a big list without any specific ordering about what we have been working on and what we're going to work on. As you might know, why did this turn off now? That is not good. Now it's on again. Weird. It's on no specific order, and anyway, let's jump right in. Of course, just a few words about what systemd actually is for the uninitiated. Systemd is the core component of most Linux distributions these days, of pretty much all the commercial ones, but most of the community distributions have also switched over. The init system means it's basically the first process that it started, but systemd is more than just a basic init system. It's actually a full suite of components that you need, like the basic components to build an OS from. That's at least how we say what systemd is, right? So that the distributions then can go take systemd, add a couple of other components, and there you go, you have your full operating system. So systemd is basically this glue that holds everything together, that sits below the apps, but above the kernel, and make sure the system runs the way it should be. Systemd started out as just being the init system, and it gained these various components because we thought that service management needed them, or because we thought that the basic building blocks of the OS should contain them. I'm not going to discuss this time what the specific components are. That's material for a different talk. I really just want to focus on what we worked on the last year and what's coming next. So, the first item that I would like to talk about is KDBus. KDBus is a kernel reimplementation of something that has been around for a while, which is dbus. Dbus itself is an IPC system, right? It's IPC's inter-process communication. It's basically how different processes on the system can communicate with each other. Dbus is, I think, 12 years old now, and it was created by the Free Desktop, or by the GNOME and the KDE people in the Free Desktop project, as a way how applications can integrate with each other. This is both for applications talking to each other, like unprivileged applications talking to each other, user applications, but also for user applications talking to the system. Since systemd is basically the system, it provides a lot of these dbus interfaces. So, dbus is a very nice design, I think. It has stood the test of time, the way it was designed 12 years ago. It's pretty much still something how we would design it today. We would start fresh with all the experience that we have. Hence, we like it a lot, right? dbus has a couple of issues though, right? It's relatively slow, and the latency is high, the throughput is low, the security mechanisms are minimal, the introspectability is limited. So we thought, it's a great system already, but let's make it better, and let's figure out where we should be making it better. And we then opted for implementing its basic semantics as a kernel module, right? Like previously it was a user space component that was basically building the IPC system. Now the screen is gone again. Which was basically building the IPC system on top of AF Unix and similar low-level Unix components. But with KDBus, our intention is to move all these basic IPC primitives, like method calls and things like that, into the kernel, so that the kernel starts to get a proper concept of what a method call is, what a service is, what a client is, like that, so that we can achieve better performance, both in latency and in throughput, and also can better integrate with security frameworks like Linux and these things, and a couple of other stuff. KDWIS is something we started a while back and posted on the kernel mailing list. It has gone through a couple of iterations now. I think it's looking better than it ever has. We kind of hope that KDWIS in a slightly modified version will hit the kernel soon. Like a couple of days ago, we moved KDWIS into Rawhide, so that the Fedora Rawhide kernel nowadays ships with KDWIS out of the box. We also changed in systemd that the user space side of KDWIS is now used by default unless the kernel module is missing or it's actively turned off. So basically, we turned it from opt-out into from opt-in into opt-out. If you understand what I mean by that, it basically means that by default it will now be turned on if all the components are viable, but you can still opt out for it. But your distributions can change this. Okay, this sounds all very confusing what I just said, but it is very confusing. Anyway, so what is the net result of all that? It is basically that we will have, for the first time, a fully featured IPC in the Linux kernel with a really good user space API. The user space API, by the way, is something that is called SDBus, like the third thing on the slides. SDBus is basically a re-implementation of a dbus client library, right? Like it's basically a library that helps you put together method calls and send them to a service, to a service on the system. Like, for example, talking to systemd. But you can actually talk to anything you like. SDBus is basically a re-implementation of a library called libdbus. Libdbus is something that is shipped along with the dbus reference implementation. There are a couple of other dbus implementations. There's like the one that GNOME uses, which is called gdbus. But this one is, SDBus is basically another one that is considerably more low-level than gdbus, but delivers what we actually needed for low-level systems development in the systemd context. Anyway, so putting that together, KDBus is hopefully something that we will be able to finally deliver in 2016. We started working on that already 2 years ago, so it's really time to actually deliver that. Anyway, that's kind of the first thing I wanted to talk about. Let's talk about the next thing. So this is a completely different topic now. It's about nspawn. Nspawn is our minimal container manager. It's a little bit like you could compare it with KVM. What KVM does for virtual machines, nspawn basically does for containers. So it's basically just this little runtime that allows you to run container images. I will do a talk about nspawn, machined and importd, which altogether are basically our solution for containerization. I will talk about that in more detail tomorrow. So if you're interested in that, please join me here tomorrow. I think at noon or something. I guess I don't want to talk too much about this right now, given the talk we have tomorrow. Let's just leave it at that nspawn is something we added a couple of years ago, mostly for testing things, because we needed to, like a way to efficiently test systemd boots, simply because, like, I mean, if you develop an init system, you keep on, you have to boot all the time, right? Like, because that's what you write, the boot process of the system. And of course, you don't necessarily want to reboot the full system all the time, because booting the physical system all the time is actually really, really slow. So we looked into ways to making it quicker for our own testing, and we thought, okay, let's make this work in containers, and let's make sure that systemd boots up in containers right away. And that's what nspawn then turned out to be. We initially tried to do this with existing container managers like LXC, but we wanted something much, much simpler, and something that doesn't need any configuration. It can boot a container image right away without modification. Anyway, enough about nspawn. Let's talk about that tomorrow. Here's another thing that we have been working on in the past year, which is systemd networking. So networking, of course, is a core component must be a core component of what an operating system does. Pretty much every system in the world is nowadays networked. Systemd networkd is what we propose as a solution for network management. It's not the first solution for this, absolutely not, but I think it's a very powerful solution, very interesting solution to admins and developers alike. It basically does what Network Manager do, or what Debian's IF up-down package do, or all the other implementations do. However, we sat down and tried to make it much, much nicer to use than the other options. Specifically, this means, well, you have these network configuration files, and they have a match section at the beginning, which basically allows you to write configuration once and apply it to as many network interfaces as you want, dynamically as the network interfaces appear. Right? Like you can basically write one network configuration file and say it applies to everything Ethernet that ever appears on the system. Or you can write a network configuration file that applies to everything Ethernet with that MAC address. In which case it would be a very specific match and not a very generic match. Or you could even say, please match against all PCI network cards. Or against this or that or whatever. The basic takeaway of that is that, yeah, you can write in very simple terms, very generic configuration. This is useful, for example, let's say you want to configure, like you want to build a networked device that implements bridging, right? And you want this behavior that whatever network interface, like a network card you plug into that system, automatically gets added to the bridge. With networkd, you can express that very simple, in a very simple way. You just drop in one network file and say, yeah, whatever it is, as long as it's Ethernet, please add it to the bridge. And then networkd will enforce that. That's actually really useful. It goes even that far that Intel has been working on actually building real routing hardware based on this. And for them, there's even a concept like uplink, downlink. So basically that the link beat on one Ethernet connection is reflected on another. Yeah, networkd has a lot of features that other solutions like network managers currently don't have. Like, it has a built-in DHCP server. It has a built-in DHCP client. You might be wondering about that. Typically heard criticism about that is why do you need an embedded DHCP server in your networking solution? Our response to that is because it's necessary. The reason is basically DHCP is one of the simpler protocols that you have in this world today. It's basically, it basically has three messages like I'd like an IP address, somebody offers you an IP address, and you take the IP address. So given how simple it is, we thought it makes a lot of sense to implement this. This is especially useful like if you have like for example one use case is containers actually. Because in containers, if you consider them like the containers pretty much full-featured hosts, then every time you start a container, it should be able to get an IP address and routable configuration, DNS server information, things like that. In networkd, because it is has the DHCP server functionality, and because you can write generic configuration that basically you say, yeah, apply this to every virtual tunnel connection to any container you run, you can basically write one configuration file and then applies automatically. And then networkd has all the logic built in. That will pick a free IP range for each interface as it appears. It will do DHCP on it. It can also do IP masquerading automatically. The net result of this is basically you get automatic network configuration in a level that was not available before, because the network manager and all the other solutions, usually like as a new network interface appears, you first have to give it some kind of configuration. Or if you don't, then it will pick some generic configuration, but which is seldom what you actually want. Anyway, I think networkd is awesome. So it has all these masquerading things, can configure IP forwarding, can do IPv6 privacy stuff, it can do this and that and everything. And it can do the uplink, downlink stuff that I mentioned. Yeah, right now, it has some serious limitations though as well. One being you cannot actually interact with it, right? It works fully automatically, so it will apply configuration as the network interfaces come and go, right? But you cannot actually tell it to configure an interface right now or not do that. The reason for that is basically has something to do with KDBus, because one of the benefits that KDBus will give us is actually that IPC will be available during earliest boot and latest shutdown, right? IPC will basically be available during the entire runtime of the system. This is not the case with classic dbus, because in classic dbus, IPC is only available as long as the dbus daemon is running, right? Coming back to network D now, we wanted to be able to run network D inside of the inner D, you know, right, very, very early in the boot process to implement things like NFS boots, like network boots from NBD or whatever, or iSCSI, whatever you like. And that basically means you want IPC, like if you want to have network D accessible via IPC, you have the problem that, well, how do you do that if dbus daemon is something that only runs during normal operation, not in the inner D? Hence, for us, always the answer was to go for KDBus. KDBus has been delayed a bit, so we'll actually currently started working on adding a proper dbus interface to network D now, which basically means that, yeah, in 2016 you probably will have a powerful network control command that will work during normal operation, but probably won't in the early boot process until the point where we can make KDBus the default, if that makes any sense. There's a question.
Hi. I have been using network D to set up I have been using network D to set up a small net. It's very good. It's awesome. But I have an issue with DNS because network D can make a DHCP server, but it doesn't serve DNS addresses. Is there a reason behind that?
So our intention there is I'm not sure if everybody understood the question. Basically, because network D has a DHCP server internally and it can serve you IP addresses and everything, most of the network configuration for a client to this should just work automatically, with the exception, though, of DNS, because DNS information is currently not propagated, and network D does not implement a DNS proxy of some form. And the solution where I would like to go to is basically that whenever network D gets DNS information from its own uplink, it will propagate that via DHCP to the clients, right? So that the clients to network D in this case, like the network Ds, for example, inside of a container, will always use the actual DNS service that the host learned about, so that there is no DNS proxy or anything like that, but everybody talks directly to the information that's available. Now, the part that's missing is that the DNS propagation actually works. The reason for that being that there are a couple of, basically we need a DHCP functionality that is a DHCP update, which basically allows the server to notify a client that something's changed and it should refresh its lease. But that's something we haven't implemented so far in our DHCP implementation. I think the big problem is not that big, because you can actually, inside of, on the host, always use a DNS server 8888, like the Google one. It will always work, right? So this is basically why we managed to just push that aside for now. But again, the solution that I really want to go to is that, yeah, whenever we learn a new DNS server, or when we lose a DNS server from uplink, we will inform all the clients about it, and they will then drop it or add it, so that you always have everything in sync and everybody uses the uplink.
So this is something that you plan to implement in the future? Yes,
it's something we want to do in 2016.
Okay, thank you.
We actually spent a lot of time already in looking into this, but we have not implemented that. But it's high on our to-do list. Anyway, so much about system network D. Well, let me say, okay, so network D is pretty useful already. Like if you have embedded devices, it's perfect because you usually don't interact with them. So the limitation that you cannot interact with them right now is not that much of an issue. It's also great in containers because it's kind of similar to that. Containers is nothing you generally talk to. It's useful in many servers because in servers it's completely okay to apply one configuration, and if you want to change it, you just restart network D and everything's fine. But it's certainly not good enough for desktop stuff because desktop stuff is highly user dependent, right? Like it's a user who clicks around in the GNOME networking UI, and we have nothing in that area, right? A couple of distributions have actually adopted System Network D now by default in their cloud editions. Like recently, Fedora made the decision. Before that, Ubuntu made the decision. CoreOS is already shipping with Network D. By default, actually, CoreOS funded the initial Network D development. Yeah, we try to push this into the distributions further, bit by bit, but the desktop will probably get it last, right? Also note that Network Manager is probably what you want to use in the desktop. right? But Network Manager, for many reasons, has probably not a very good reputation for being run on the server. Anyway, so much about networkd. It's really awesome technology. If you build something with containers, build something with embedded devices, have a look at it. It's really, really nice. Next component I would like to talk about is systemd resolved. Systemd resolved is another component we recently added. It's it's basically a DNS resolver caching daemon that runs locally. You know DNS, right? DNS is the thing that translates names into IP addresses. Traditionally, the job of translating names to IP addresses was implemented in libc, right? And so that every process that was run when it wanted to resolve a DNS name would run its own little DNS stack embedded into the binary talking to the internet. It would not employ any local caching, well, if there was a bug in the libc DNS implementation, all processes that ever did DNS would be exploitable, which is quite a limitation. So with systemd resolved, we try to fix a lot of that. Systemd resolved is basically a small daemon that runs locally and whose job is to do a DNS resolution so that clients, when they want to resolve a name, don't go directly to the net with the internal DNS stack, but just ask this local daemon, and the local daemon does it for them. Systemd resolved, so it's already a security benefit. It's a caching benefit because resolved caches heavily. But it also systematically solves a couple of problems we always saw with DNS resolution. Specifically, like if on my laptop, for example, I work for Red Hat, right? And that means that from time to time I log into the Red Hat VPN, right? The Red Hat VPN has a DNS server, and that DNS server has a couple of domains defined that are private to Red Hat, right? That are not visible outside of Red Hat, right? I also, when I do that at home, I have a local network. In that local network, I also have a couple of DNS names defined, one for my printer and one for my router, for example. Because in traditional Linux, you could have one DNS server at a time, that was used at a time. The result was I could either talk to the Red Hat servers or to the local servers in my local LAN by name, but not to both. And that is quite a limitation. It's like the split horizon VPN problem, right? Like that as long as you're in the VPN, you'll only see what Red Hat wants or your VPN provider wants you to see. And while you're out of it, you will only see what the local LAN has to offer. With systemd resolved, we try to find a way how we can make this work more nicely. So the logic we implemented is actually that DNS servers are strictly assigned to specific interfaces. And when we do want to resolve a DNS name, we will actually do the query in parallel on each interface, right? So in the VPN case, again, this would basically mean if I want to resolve the name foobar, I would do so in parallel on the Red Hat VPN and on the local LAN. And then, when I get a reply, like the first positive reply wins or the last negative reply wins, right? Which has the effect that the name resolution of the zones of the VPN and of the local LAN are implicitly merged, right? And everything stays resolvable. Yeah, something like this we implemented. There's more that we want to implement in this area, like, for example, DNSSEC. DNSSEC is this cryptographic extension of DNS that actually makes DNS lookups cryptographically verifiable. This is something we're currently working on. Actually, I just, the hour before I came here to this talk, I was reviewing the first set of patches for that. So with DNSSEC, our idea is basically that, yeah, DNSSEC should just be the default on Linux systems because we live in this world today where DNSSEC is actually deployed on the internet and where everybody deserves the security that this brings. Resolved also implements a protocol called LLMNR in addition to classic DNS. LLMNR is something that Microsoft invented. LLMNR stands for Link Local Multicast Name Resolution. It is something that Microsoft invented for connecting small devices together in a way via IP, in a way that they can find each other by their names, right? Which is, with DNS, it's always problematic because DNS names are registered in a central server, right? And if I build an ad hoc network between two small devices, then of course I will not have a DNS server where I can add this to, and there will be no administrator. It will just exist for 5 minutes or something like that. So a different solution was needed. Microsoft came up with something called LLMNR. And with LLMNR, basically, every host in this little network knows his name. And when one host wants to contact another, it asks on the network, okay, what's the IP address of the host with that name? And then that host replies, and you can connect to it. It's basically something that is similar to a protocol called MDNS, if you might have heard of that. That is basically, MDNS is something that Apple came up with. LMNR is the Microsoft version of it. It's very, very similar, but also very different. Our intention with ResolveD is to support both protocols so that host names will just work, and they work in a way that they're compatible with both macOS and Windows. And that's actually really useful. It's not only useful for this use case of actually connecting to end-user devices in an ad hoc network, it is also useful actually in containers, right? Because in containers, if you have containers on a server and you run like 5 containers and you connect them via a virtual link, you want this functionality that the containers can find each other. And for this, I think System ResolveD is a really, really nice solution because every container can just know its own name, and System ResolveD will make sure that the names are resolvable between the containers in this virtual link. And even better, you could even add to that virtual link, let's say Windows VM or something like that, and because Windows supports the same protocol, suddenly all the name resolution works between them as well. So yeah, that's System ResolveD. We so far have not pushed it into any of the distributions. The reason is, it's available in most of the distributions, but it's not the default. We want to make it the default, but for that to actually make it interesting for distributions to adopt that, we actually need to provide something that is substantially better than everything that was there before. For us, that big thing that we think we can convince the distributions with is going to be DNSSEC, because currently the DNSSEC situation in Linux is not very good. And as soon as we have implemented that in System ResolveD, we can tell people, okay, look at this. This is substantially better. It gives you DNSSEC in one unified solution. Please consider adopting it. We kind of hope that this is going to be adopted in 2016 in the big distributions. Here's something smaller that we recently added to Systemd. It's NSSMyHostname. It's a very little program. It's NSS is the name service switch of Linux. NSS is basically how host names are translated, right? There's one module, NSSDNS, which translates host names to via DNS to IP addresses. But NSS can actually get data from any database you like, for example, from etc hosts, which is also a very common source for host names translations. And then there's NSSMyHostname, which resolves exactly 3 host names. It will resolve your local host name, whatever you configured it to your local IP addresses. It will resolve localhost to 127.0.0.1, and it will resolve the host name called gateway to your local IP routing gateway. And that's all it does. It's very simple, but very, very useful, because it gives you this guarantee that, your local host name is always resolvable. You don't need etc hosts around anymore for things to work. And if you want to know your gateway, you can just type ping gateway, and we'll see if you can reach your gateway. I hope that makes any sense to you. But it's a very, very simple thing. I like it a lot. There's also a related NSS module we also ship. Like NSSMyHostname is actually turned on in most of the big distributions, at least in Fedora. In Fedora I know for sure, but I think the other distributions turn it on by default too. NSSMyMachines is also an NSS module. It also provides hostname resolution. And what it actually does is it provides hostname resolution to all locally running containers, right? So if you have 5 containers running locally, and each of them has an IP address, NSS, and they register with the system, then NSSMyMachines will actually make their names resolvable without requiring DNS, without requiring LLMNR or anything else. The idea basically is NSSMyMachines just makes things work. Here's something else we have been working on, which is an integrated service firewall. So the idea is basically, like most of you probably, at least the ones who have been administrators in one life or currently, is a firewall you configure locally, right? Then you specify, okay, this port is allowed, this port is disallowed. We thought when we looked at the problem that, okay, actually binding these rules to ports is probably not what would be the best solution, but instead we should be able to write rules that apply to specific services, right? So that you can say, okay, it's not about people shall be able to connect to port 80, but instead you can write people should be able to connect to Apache. Yeah, you see that the semantic difference between binding these things to IP ports to binding things to actual systemd service names. We looked at this. On one hand, we really didn't want to become the firewall of our own. We had no intention to actually do that. But what we want is to have this link that you can link up the systemd service information with the firewall. And we have actually implemented that pretty much completely. Like if you look in the GitHub repo, you'll find that. But it's currently, the functionality that we need for that is currently broken in the kernel, and we're waiting for the kernel to fix that. As soon as the kernel is fixed, we'll land that in systemd. So basically what this will enable you to do is that in the systemd unit files, you can then start configuring firewall semantics with a very, very simple syntax. You can just write firewall accept, or firewall deny, or firewall reject, like equals. Meaning basically that, yeah, Apache shall be able to be talked to, shall not be able to be talked to, should generate an error when you try to talk to it. And there's also going to be the special setting firewall equals custom. If you do that, then the effect will be, I mean, if you know IP tables, you know this concept of chains. If you specify firewall equals custom, this will then have the effect that all the traffic coming in and going out for that specific service will be forwarded to a specific chain that is named after the systemd service that you do. This basically allows you to write your own firewalls rules with IP tables. You just have to label them under the right IP tables chain, and the systemd will forward the traffic to it. It's a very simple way how you can hook up basically service management with firewalls, because like at least we think that's actually what most people want to do. Yeah. Something else we did, we hooked up auditing with the journal. I'm not sure if you guys know auditing. Auditing is basically something that the three-letter agencies of this world ask for. It's basically, it's a way how you can generate a special kind of logging events whenever security-relevant things happen on the system, right? So this could be like auditing events, like there are quite a few different auditing events defined. One of the more useful ones is actually via auditing you can make it happen that every access to etc passwd generates a log message. So that the admin can install this rule, say, okay, whenever etc passwd is read, it's written to, it's manipulated, whatever, please generate a log message, and the kernel will then enforce that and do that, right? Auditing has been around for a long time, but nobody knows that it exists, and it's awful to use. But we thought, okay, auditing is just one special kind of logging, and we should probably just hook it up with the journal and make it available like any other kind of logging on the system, right? Because, I mean, well, let's take a step back. I'm not sure if you guys know the journal. The journal is basically the logging component in systemd. Every message in a systemd system that is logged will end up in journald sooner or later. So regardless if you have a service that logs via classic syslog, or if it just writes something to std out and stdr, or if it's a kernel, it all ends up in the journal. And with this change, the audit logs will also end up in the journal now. The net result of that is basically that whatever happens on the system, regardless if it's in the early boot, in the late boot, regardless how it is logged, it all ends up in the journal, and you will have a unified, strictly ordered stream of logs, regardless of the type, regardless of the source, regardless of the time of things to look at it. And the idea is then, of course, always that of course, you not always want to see the audit stuff when you look at it, but the idea is that you apply filtering while you view it instead of filtering while you store it. By the way, if anybody has questions, completely interrupt me, totally do that, because I only have 10 minutes left. I mean, I have much more slides here, actually, than we probably can cover. So, but I would rather have it if people ask questions than me just continuing with the slides. But nobody has questions. Then go to the next slide. So one more component we recently, there was one? Where? Oh,
there. Hi, Lennart. I'm also giving a talk on containers tomorrow, So I figure instead of doing research, I would just come here and ask myself. This question may be more appropriate tomorrow, but since you're talking about the future, I wanted to ask you about the Open Container Project. And
let's talk about that tomorrow.
Okay.
Okay, then let's talk about the slide unless anybody else has a question, except for the container questions. The container questions, please, let's talk about that tomorrow. No other questions? Okay, then let's talk about core dump. Like we have the systemd core dump thing recently added. Systemd core dump, you know what a core dump is, right? Like if a program crashes on Linux, it will generate a core dump. A core dump is basically an image of the process when it died, and you can pass it to your debugger of choice, like to GDB, and it will tell you exactly where it crashed and what the memory looked like when it crashed. Core dumps have been around since Unix began, basically. With a systemd core dump, which is a component we added, now whenever one of these core dumps happens on the system, systemd will automatically generate a backtrace out of it, you know, like a stack trace, and will write that as a normal log message to the journal, right? That way, core dumps become pretty normal loggable events. Like they're just loggable events like any other. They happen to have a core dump attached, but if you centralize your logging, you will just see the stack trace right away. We then added a tool called core dump control. Core dump control is something that basically just asks the journal for all the core dumps that happened in the recent times. We'll show you a list of them. And then it has a couple of commands to actually introspect them and see what actually happened. And it even has one command that's called core dump control GDB. And if you type that, it will actually start GDB for the last core dump that happened on the system and pass a core dump to it so that it will actually immediately can check what's actually going on. For developers, it's actually really, really awesome to use. So if you are a developer, please have a look. It's awesome. Unfortunately, it's not adopted in Fedora, for example, because in Fedora we use something called a board. I personally think that systemd core dump is a much more convincing solution than a board. But of course, it's for everybody to decide. And Fedora likes a board, apparently. Anyway, it's a really, really cool tool. Please have a look. Something else we have been working on is actually the entire story around EFI and systemd boot. EFI, as many of you probably know, is like this firmware interface. Like it actually stands for Extended Firmware Interface. It's basically the replacement for the classic BIOS. With systemd we have this vision of creating an operating system that is fully trustable, right? Like so that in a world where you know, with the Snowden revelations and things like that, you cannot really trust anymore the vendors or the communication with the internet. We thought we would like to go towards a system where the firmware verifies that you can only boot the operating system that you chose it to boot, right? So that there's cryptographic verification, for example, that you say, okay, I only want to be able to boot my operating system if it's signed by Fedora. And that if you say that and tell the BIOS that, then it should refuse booting anything else, right? So this gives you a security in regards that, if you leave your laptop somewhere and somebody wants to install a backdoor, he can't do that anymore because he would have to get his backdoor signed by Fedora. Of course, Fedora will not do that, and hence you get some extra safety. I think in the long run, this is something that's not only useful for laptops and like these devices, it's also very, very important for servers because as you know, with the NSA revelations that the NSA had access to the Google data centers, for example, and so if you with this kind of stuff, you can basically say that, okay, I have my gigantic data center, I have 5,000 machines there. In these 5,000 machines, I want to make sure that it only boots my operating system and nothing else, so that you don't really have to trust the guys anymore who put the computers in the racks, because they cannot manipulate things anymore, because the machines will only boot what you prepared and not what they try to sneak in and try to backdoor on the system itself. So with systemd, we have been working in this direction. So there's a tool now in systemd that you can use that builds one EFI binary, like one thing that you could start at firmware times, out of a Linux kernel, a Linux initrd, like the first bits basically that the operating starts, boot splash, and a little bit of meta information. You can turn that into one EFI binary. You can sign that cryptographically, and then you can make the BIOS boot that. And because it's signed, and you can enroll the key for the thing in the BIOS, you basically have a nice way how you can do proper authentication of whatever is booted. There's also a component called systemd boot, which can go through all these images that you generated this way, can extract the meta information, shows you a pretty menu, and then you can select one of these and actually boot them. Systemd boot is basically something that used to be called Gummy boot, if you ever came into contact with that. We changed it a little bit around and moved it into systemd in this context. Systemd boot is supposed to be extended very soon to do more than just being a boot menu, in regards that it can actually count successful boot attempts. The idea basically being that we come to a state where we can do completely automatic system updates with a fallback if the new boot up doesn't work, right? Like, I mean, the background of this is, you might know the Google Chromebooks. The Google Chromebooks have this, like, what makes them so good in a way is that they automatically update their software all the time, right? Like, they automatically download new software versions in the background, they put them on the disk, and then just by rebooting, you boot into the new software version. But if you do this, right, like this kind of automatic software updating, you also need to make sure that if you roll that out to customers, that you don't break their systems, right? Like, software always has bugs. If you roll out things to people, you need to make sure that there's a sane way how you can get back to the old version if the new version breaks for people, right? And so Chrome OS came up with this boot scheme where they basically say, okay, we boot up the computer once. If it works, great. If it doesn't, we try to reboot it once more and once more. If it fails 3 times, we go back to the old version. That's an awesome feature of Chromebooks, and we thought, okay, we want that on generic systems too. So we added that to systemd boot, basically, or to the old Gummy boot. So it's not just a boot menu, it's also something that's supposed to help you if you want to build devices, either end-user devices or embedded devices, that you can centrally update in a nice and reliable way, and can be sure that the system automatically rolls back to an older version if things don't work properly. But yeah, the stuff with the counting things is still something in progress. It should end up in the systemd tree either in the next months or early 2016 or something like that. But anyway, the general takeaway of this is that we will come to a system where we can actually do these upgrades automatically and securely, and where we want to enable users to either lock out, for example, Microsoft from the machines, because then nothing can be booted anymore on your machines than what you chose, or you can even sign your software all on your own, and thus make sure that, yeah, everything that you wrote works fine, but nothing from anybody else. I think I don't have that much time left. Let's do more questions if anybody has that. I know this was all fairly technical, but I hope that they're good questions.
You made a post blog last year about your vision with systemd and B3FS and stateless system. What stage is that idea right now?
That's a very good question. We have worked in some areas, but it's not ready yet. So we, like in systemd, you have a lot of components like how you. Okay, so let me take a step back. The question was about something. I talked at Guadek about a concept about stateless systems and apps and things like that, and the question was really just about what the state of that is. By stateless systems, we in the systemd project at least think of systems where basically the entire operating system is monopolized and /user, or like USR, and where etc and var don't have to be around to be able to boot, and where if etc and var are missing at the first boot, they're automatically created and populated with the little bits that are actually necessary. So yeah, we started to fix a lot of the basic building blocks, but it's still a long way to go, because I mean a lot of the software is ready now, like of the really basic software is ready now to work in a way where etc is empty or where var is missing. and where they will recreate in Etsy what's missing if on their own or in var. But there's still so much software that is not ready for that. And only after we did the basic building blocks, we can go to the next step with the apps. Some people in the GNOME community, most notably Alexander Larsson, is actually working on the sandboxing stuff already in a slightly different context. So if you care about the app side, more of that. There's some progress on our side, but it's still not, it's far from ready. Like very recently, the most recent changes that we did is like dbus, for example, which was one of the biggest problems we had so far, is now capable of booting without Etsy, and PAM also got fixed. So those were the two biggest outstanding building blocks. Net result is, if you have a Fedora, and you have a very minimal installation of it, you can get the stateless stuff to work right now. But it's not officially supported by Fedora yet, but we're getting there. It's a massive effort. And again, I'm sorry for all the super technical stuff, but I hope it was anyway exciting. At least it was exciting for me.
Hi. This sounds, it's a simple question. It seems like UEFI Boot, systemd boot, it will replace or render grub basically useless in a way that will be replaced. No need to have grub installed anymore. Is that it?
So, I mean, grub is something, it's like the grand unified bootloader, right? Like grub supports almost everything in the world that you want to boot. Like it can boot from everything, and it supports every boot protocol there is. Like what boot kernels you have, and from the firmware side. Gumi boot or systemd boot focuses exclusively on EFI, right? It will not boot on anything else. It uses EFI concepts like secure boot. It uses EFI concepts like the EFI binaries. That makes it very, very simple, right? Because it's really just a menu that can count. Yeah, I think effectively, like at least the bigger systems, right? Like bigger embedded systems, server systems anyway, desktops, they all focus exclusively on EFI for newer systems. And hence, I think systemd boot is probably good enough for many cases. I know that Intel is actually building Gumi boot nowadays in ARM phones, like ARM phones that come with EFI. So I'm pretty sure that by focusing only on EFI, we can make our system so much simpler at the price that some embedded hardware, some old hardware will not be supported, but we will support the vast majority of new systems that there are.
So again, on DNS, you said about Resolve D, and it's a good addition, but it's implemented on libc, as you said. At this moment, the first time a program starts, it reads the etc resolve conf, and then it caches on the binary, as you said. How Resolve D will be implemented? It will be in the libc, or it will be implemented as a local DNS server?
So, you know, I already showed you two NSS modules, right? Like the MyHostnames and the MyContainers. There's basically a third one, which is NSS Resolve. And it basically is like, it replaces NSS DNS. NSS DNS is this internal implementation that the libc ships that does DNS stuff, and it basically replaces that and instead talks to Resolve D, like this little daemon. So that's how we hook up libc and get adre by name, no, get adre info, like the commands, and get host by name and these things with Resolve D, simply by providing the NSS module that hooks it up. How much time do I have? I think I must already be over. Okay, this sign says time is over. So if you have any further questions, then do catch me in the hallways. I'm happy to answer any questions you might have. Thank you very much for your time, and come tomorrow for the container talk, please. Thank you.